and welcome back to Survey Science 2021. Hope you've been enjoying so far the presentations and you've been able to join as many talks you like. If not, just remember that in the members area of the webpage, you can find all the talks on demand. So this is session 5. We have 3 talks this morning. The first talk is by Lars from Sintef in Norway. And I don't want to take too much time from him. So Lars, all yours.
Hello. So my name is Lars, and I'll be presenting our paper on tool-assisted threat modeling for smart grid cyber security. First, I'll give an introduction. Then I'll move on to the template that we have created. Then introduce the use case, which we use to illustrate the use of the template. Move on to a discussion, and finally I will have some quick slides on how the template may be further developed and expanded by others. So as we wanted to contribute to the cybersecurity of smart grid, and more specifically to the threat modeling of smart grid. This is something that has been done already, for instance, using methods such as Stride, Petri nets, and tech trees. But we have observed that most of these methods are manual and that they often concentrate on specific parts of the smart grid or specific components, for instance, the smart meter. We have used the Microsoft Threat Modeling tool, which is a tool that can be used both to create a template and then afterwards to do threat modeling with the created template. And an overview of the threat modeling tool and the ecosystem can be seen here in this figure, where we have the threat modeling tool from Microsoft, a number of templates, which can then be applied to applications or use cases. And our contribution is then marked in green here. And the advantage of this is that it does also rely on Stride per interaction, but it allows for automatic threat generation. And we believe that this will help to make the process of threat modeling more efficient, but also make it more, or improve the quality in the way that threats can be automatically detected and probably less likely to be forgotten. So now I'll say something about the template that we have created. Since the threat modeling tool relies on Stride, the model is created using data flow diagram elements. Selection of the data flow diagram elements that we have included can be seen to the right here. In the middle, we have an example of a threat model where a SCADA server communicates with an external network and with a database. So the elements are the classical data flow diagram elements. However, their interpretation varies a bit from the classical software-driven Stride threat modeling method. Especially this is the case for the process element, which normally would be used to describe a software process. However, in our template, we have chosen a higher abstraction level, and here it is used to describe a system of components or systems, essentially. Another example is the data store, which traditionally can be used to describe both databases, memory or files, and in our model we only include the database. The files or memory are assumed to be part of the process elements. Then in addition to the data flow diagram elements, we have the trust boundary, which is used to separate more trusted elements from less trusted elements. Finally, I'll say something about some additional design choices that we have made for the template. We focus on cyber threats and more specifically on remote cyber threats. This means that we do not focus on remote threats. We do not focus on internal threats. We do not include physical threats, for instance, sabotage. We also do not consider threats such as natural failures or wear and tear and such. Now, also say something about the threat generation, which is a key part of the template. So threats are generated by considering instances of a source, a flow, and a target. In this example, we have an external network, which is communicating with a SCADA server. And then in the creation of the template, the creator is free to assign certain properties to these elements. And then afterwards, in the threat modeling, when the model is created, these properties can be given certain values. And based on a logical or a Boolean expression, which is included by the creator of the template, it is decided whether the threat is included in the threat model or not. Now I'll say something about the threats that we have included. So for now, we have around 40 threats. And they are categorized according to the STRIDE categories of spoofing and tampering and repudiation and so on. These threats are inspired or taken from literature on smart grid threats, from other Microsoft threat modeling tool templates from other domains, and to a lesser degree from previous attacks on industrial control systems. And some of the threats can be seen to the right here. For instance, we have a tampering of communication, GPS spoofing, or TCP or IP flooding. And as we see, there is a mixture of more specific and more generic attacks. So the tampering of communication is quite general, and it's included to encourage a reflection on how that threat may arise. And while the more specific threats can be regarded almost as a checklist to make sure that these threats are handled. And now I'll say something about the use case which we used to illustrate the use of the template. The use case here is taken from the smart grid, and we have two operators here, a transmission system operator and a distribution system operator. They control each of their part of the grid, the high voltage and the medium voltage part. And they both communicate with an intelligent electronic device, which in turn also communicates with a measurement unit. The distribution system operator also controls windmill here, while the transmission system operator controls the voltage source. So then we take this physical system and we attempt to model it in the threat modeling tool. And that gives this model here, where you can see that we have the SCADA server here, and the distribution system operator server and the transmission system operator. They both communicate with their I&D processes. The distribution system operator communicates with the windmill. They both are assumed to have a human operator. And then this model can be created by an easy drag and drop from the list that I showed earlier. And then the various elements and flows are given certain properties, or the properties are configured to reflect the actual system in the best possible way. When this is done, the tool can be asked to generate threats. And in this case, it generates a total of 334 threats, which is quite a lot. And it should also be noted that the type of threats and the number greatly depend on how we choose to configure the system. Now I'll move on to a short discussion on the template that we created. So in a model like this, there will be some false positive threats and some false negative threats. And by false positive threats, I mean threats that show up in the model but are not present in the actual system. and by false negatives, threats that are present in the actual system but do not show up in the model. And we attempted to minimize the amount of false negative threats, and the reason being that we believe that false positive threats can more easily be discarded by the team performing the threat modeling, but it may be harder to come up with the threats that do not show up in the model. And one way we attempted to do this was by generalizing the threats we found, so that they affect many stencils, many of the elements in the same way. And this also caused many of the processes to be rather similar. This is because what separates processes from each other are the properties that they are given, and the properties are very relevant for the generation of threats. Another thing we did was to set the default value of the properties in such a way that the maximum number of threats will be generated. The reason for this being that if an element was included in the model, but it was not configured, then as many threats as possible will still show up. What I've also already mentioned is the large number of threats that are generated. So for our model, that was a total of 334, which is quite a lot. And we have found a few good ways to automatically classify these threats, meaning that the team doing the threat modeling will have to go through the list generated and manually classify them, for instance, according to priority, decide whether they are relevant or not, and decide whether they are already mitigated, and then provide some justification for that. What we also have in the model is the trust boundary. However, we only have one, which means that we either trust or do not trust. There are no degrees of trust. And this deviates a bit from other models we have seen in the threat modeling tool, which have various degrees of trust. And finally, the model is uploaded to GitHub for those who may want to use it or further develop it. And I will show some slides at the end on how this may be done. And then on to the threat modeling tool itself. It has certain advantages and disadvantages. Among the advantages are the high degree of freedom that the creator of the template is given. One can choose exactly what sort of elements should be included, what kind of properties they should have, what values these properties may take, and also include other degrees, other categories of threats, for instance. For instance, if you would like to also simulate physical threats, another category could be added for that. Furthermore, it allows a very structured way to do the threat modeling. Once the threats are generated, a list is shown, and the team doing the threat modeling can go through this and determine what threats are relevant, what are not, and provide justification for the choices being made. And when this is completed, the tool will generate a document giving a nice overview of the identified threats, which threats needs further investigation, and also on the state of cybersecurity of the system. Finally, the tool allows for the merging of templates, meaning that this template can be merged with another template. For instance, the Microsoft Azure template for use cases where both of the stencils or both of the elements from both those models are needed. Among the disadvantages are that the tool only allows one level of inheritance for the elements. So this has not been a big issue for us, since most of our properties and the threat generation is located at the parent level, but still the reason for this is not evident. And furthermore, included properties are regarded as global, meaning that different classes, so to say, of elements cannot have properties with the same name. As already mentioned, the generation of threads are closely tied to instances of source, target, and flow. Meaning that in case you would like to generate threads based on only one of these elements, that might be problematic. We would have liked to include the possibility of a forgotten VPN connection. So I forgot a VPN connection included by the vendor, but that the asset owner may be unaware of. But since this only applies to the target element, this thread was generated multiple times, and one time for each flow going into the target. Then I'll say a little bit about stride as the method for the smart grid. So I would argue that this is also quite a structured approach. Once a model has been created, every element and every data flow between them are considered, and making it less likely to forget any threads. So when this is combined with automatic thread generation, as it is in our template, and we believe that the probability of forgetting threads or not including threads are even smaller. A problem of stride is that it does not help in evaluating the probability or the impact of the different threads. So this is left entirely up to the team performing the thread modeling. And this is also a hard thing to do. For instance, one may argue that the impact of a threat may depend on, for instance, what sort of redundancy is present in the grid at the electrical level. Furthermore, software stride is traditionally a software method which we now apply to the cyber physical system. And this has some challenges. So as already mentioned, our elements have a higher abstraction level than normally. And this can be illustrated by this figure, where a windmill can be expected to contain several other components, for instance, an RTU or measurement unit. And these in turn can be expected to have several software processes running on them. So if the models earlier should have been modeled in the traditional stride way, it would have grown very complex quite quickly. And the cost of this is, of course, that you are unaware of what might happen inside the elements. So the models, the threads arising between these elements are not included. Yeah. It would also, of course, also be possible to create a model only for these elements, and that has already also been done previously by others. Another disadvantage I can mention is that stride relies on the data flow diagram elements, and an issue with these that has already also been highlighted by others is that they do not tell you how they rely on lower level abstraction levels and the security mechanisms provided by lower level abstraction levels. For instance, for the communication here, it's hard to know what protocols are used and what security mechanisms are implemented here. We try in our model to mitigate this by including a set of properties that will describe the protocols used and whatever security mechanisms may be implemented. But one may argue that this is a sub-optimal solution. And finally, I will move on to say something about how new threads may be added to the template. As already mentioned, the model can be found on GitHub. So what you then do is to download this Microsoft Thread Modeling tool and open the template. And here you may be able to include new thread types, either new categories or new thread types, and then also elements or thread properties. And this will look like this. So for threads, you give it a name and include a Boolean logic to whether it should be included or not. and then include the description of the thread. For an element, a name is included, and then different properties and the values that these properties may take may also be included. So that concludes my presentation. Thank you.
Thank you, Lars. That was that's a very interesting approach. Okay, just remember to the attendees that you can write your questions at the Q&A at the bottom of the screen. Meanwhile, I mean, you mentioned that you can classify the threads automatically. How you do that?
So the threads cannot really be, or we have not found a good way to classify the threads automatically as into various categories. This would be desirable, for instance, an automatic way to determine the impact of a thread. What the tool is able to do is to automatically detect what threads may be present in the system.
Mm-hmm. Okay. So when you mentioned the disadvantages, you mentioned, for instance, that you can have only one level inheritance. Is that a fault from the implementation, or is that a limitation from the Microsoft DMT framework?
That is a limitation from the Microsoft tool. Yeah.
Okay. As well, you mentioned that you need to specify source, target, and flow for each of the attacks, I guess. How the system is dealing then with some distributed attacks?
You mean, for instance, as a distributed denial of service, for instance?
Yeah.
Yeah. The way we have tried to model that attack is that we have an external actor element that we call an external network, and then we use that as our source, basically, and then they use a flow to connect that to the potential target. And then when in the threat generation logic, we include this, for instance, the distributed denial of service attack, if the source is an external network or the internet.
Mm-hmm. Okay. I think you mentioned as well that right now you are only dealing with external attacks, right? Mm. So you cannot deal with insider threats, for instance. What's the difference, or what should change in order to deal with insider threats?
The reason that we do not deal with the insider threats is basically a design choice. One could also include such threats. It would only mean adding new threats and new threat logic. For instance, one could say that these human operator external elements, as I showed in the model, may try to install malware on the server, may try to configure the system in a malicious way. So it's absolutely doable. We just have not done it yet.
Do you think that in that case you will be more prone to have more false positives?
The case with internal internal threats is that they can basically do a lot of things, and it might be hard to model all the possibilities they have to maliciously abuse the system. I would perhaps be more scared of false negative threats, as the operators can be expected to know the system very, very well, and may find new and inventive ways of causing harm.
Mm-hmm. Okay. So we have another question from the chat. So how does your work compare with other available threat modeling tools like Iris? I don't know about Iris, or maybe the Dragon threat modeling.
The first one you mentioned, I am also not familiar with. With the OWASP threat modeling tool, I have not used it, but as far as I've understood, it works in a quite a similar way. One difference is that the OWASP, as far as I've been able to understand, is that they have more general threats. And this is also part of their design philosophy, I believe, not to have very specific threats, but rather more general and use this to help the thought process of identifying threats. So in our model, we have attempted to do both. Both had to have general threats and more specific threats. And what also perhaps separated that is that the threats that we have included in the model are identified from smart grid relevant sources, so specifically for the smart grid.
Mm-hmm. Okay, that they provided the link to that threat modeling framework. You can take a look later. So I guess that just the last question to finalize the presentation. So just to close this circle, so you are doing automatic threat modeling, right? How difficult it would be to do automatic as well prevention? So after automatically detecting the threats, automatically defend against them.
I think the most the easiest way, at least from the perspective of this tool, would be to first of all include, or the first step I should say, would be to include possible countermeasures in the threat description, and try and suggest solutions where of how these threats may be mitigated. Yeah.
Perfect. So yeah, I think that we can leave it here. Thank you, Lars.